Just going to read this question, add to the diagram as I go. So one end of a light and extensible string, as shown, is attached to a particle A of mass 2 kilograms. So I'm going to put the weight onto my diagram, all the forces we should add. Going to be 2g. The weight is the mass times gravity. The other end of the string is then attached to particle B of mass 2.5 kilograms. So that's 2.5g. I've added the weights for A. I'm also going to add the normal reaction, which is going perpendicular to the slope, and I'll call that R. There is no more normal reaction on B because it is suspended in the air. We're told that particle A is in contact with a rough plane, so just going to kind of underline that. I'll come back to that. Cos theta is 4/5. So if I draw a slope, this is a slightly smaller version of the slope that we've got. I can put theta here, and then we've got 4 for the adjacent, 5 for the hypotenuse. This is a 3, 4, 5 triangle. Or if you don't spot that, you do 5 squared minus 4 squared, square rooted. You get 3, which gives us sine theta is going to be 3/5. These are the two we need for these kind of questions. We don't need tan theta. The string is taut. Okay, what that means is there's going to be tension in it, and it's that's going to keep B from just falling due to gravity. I'll call that capital T. And then the thing that stops A from just sliding down the slope is going to be a tension that's equal, but going up the slope. So I can add that. I'll just underline that. Passes over a small, smooth pulley at the top. The part of the string A to P is parallel to the line of greatest slope, so tension is acting like directly up the slope. Particle P hangs freely, but below P it's a distance 1.5 meters above horizontal ground, as shown in the diagram. Now, the only other thing I'm going to add is theta here, because we have a small triangle, so the top angle is 90 minus theta, and then this is a right angle, so I get theta there as well. Coefficient of friction between A and the plane is mu. The system is released from rest. Okay, that's going to be important. So all the initial velocities are 0, and the subsequent motion PB hits the ground before A reaches P. So B is moving down, and A is going to move up the slope. Notice the forces I'm doing filled in arrows, motion I'm just doing with normal arrows. And we're told that at the instant it hits the ground, it's going to be moving at 1.2 meters per second. Okay, I'm not going to add that to my diagram. I'm just going to underline it in red. Although A will also be moving up the slope with that same speed. Now, what that means, coming back to friction, is that friction opposes motion, and there's going to be a frictional force acting down the slope. All right, it's taken a bit of time, and you don't have to do this all straight away. I just think it's quite good to get as much done as you can, but we are well set up now for this problem. So part A, we're going to focus on B. We're going to apply SUVAT going down, because we're being asked about the acceleration, and we've got the final velocity, 1.2. We've got the initial velocity, it's just at rest, 0. And we've also got the displacement, which is 1.5. So I can fill these in. I want A, so I'm going to use v squared. The one that doesn't involve t, v squared is u squared plus 2as. So 1.2 squared is going to be 0 plus 3 times A. And therefore A is going to be 1.2 squared divided by 3. And we just need to show that that is 0.48. Sorry, that was from another question. 0.48. Right, let's move on. So I'm just going to reproduce my diagram here. It's a bit more space now. So remember, we've got 0.48 going down. I could add that on. I don't think I will. I think it's to the right. That's fine. Okay, part B. For the motion before B hits the ground, show the tension in the string is 23.3 newtons. So again, I'm going to focus on B, and now I'm going to apply F equals ma down. So that means 2.5 G minus the tension is going to equal 2.5 times that 0.48 we got before, which means I can rearrange tension is going to be 2.5 G minus 2.5 times 0.48. And we're hoping that's going to be 23.3. Brilliant. We're now asked to determine the value of mu. So I'm going to have, it's going to be quite a lot involved now for this next part. Okay, so let's take a look at A. And then first of all, we're going to apply F equals ma perpendicular to the slope. I need to get some information on R because that is then going to go into finding the frictional force. Actually, I don't want to apply F equals ma. I just want to resolve. It's slightly different. I'm just going to say that the forces are equal. So R is going to equal 2g cos theta. I've done that quite quickly. You've got to try and learn, in my opinion, the fact that if you kind of turn your hypotenuse into the angle, it's going to be the adjacent, it's going to be related to cos. If you're not happy with that, then I will show you how we could draw a little triangle. So I've got my 2g, remember, that's the hypotenuse. I'm trying to split it into perpendicular and parallel to the slope. So I can draw a little triangle like this. This is my right angle, and the one I want is this one here. There's theta. So you can see now it's the adjacent. You could write down cos theta is the missing side divided by 2g, rearrange it. So the missing side is 2g cos theta. And remember, cos theta we've talked about is 4 over 5. So I'm going to get simply 8 over 5g. I'll just leave it like that for the time being. Okay, that's good. Now we can investigate friction. So friction in general is less than or equal to mu r. However, in this case, it's moving, so we can say that F is equal to mu r. Therefore, in this case, it's going to be 8 over 5 g times mu. Remember, mu is what we're trying to find, so that is the only missing thing in the equation. Okay, I can now apply, I'm still dealing just with A, I can apply F equals ma up the slope. So it's going to be tension, which is 23.3. Remember, we found that previously, minus the frictional force, 8 over 5g mu, minus 2g sine theta. So we've already talked about cos theta being the one that's perpendicular. Sine theta is then the one that's the opposite, so parallel to the slope, that one there. And that is going to equal 2 times A, which we found previously, 0.48. I'll just run out of room, so just one sec. Okay, everything is known except mu, that is 3 over 5. So I'm just going to get 8 over 5g mu by itself. That is going to be 23.3 minus, this is going to become 6 over 5g minus 2 times 0.48. And then I can just times by 5, divide by 8, and divide by 9.8. Just do it carefully. Okay, so that's 10.58 times by 5, divide by 8, and then divide by 9.8, which gives us 0.6747, which I'll round to 0.675. Okay, so we found mu. Got one last little bit to do. After B hits the ground, A continues to travel up the plane before coming to instantaneous rest. Determine the distance that it travels from the instant that B hits the ground until A comes to instantaneous rest. Okay, we don't have to think about the part where it's moving up as B is falling. It's just from the moment that B hits the ground. So what is going to happen here is we're going to have the slope again, but we've just essentially got A by itself. It's this string is now slack, so I can either just ignore it or draw that in. Okay, I'm just going to ignore it. We've still got the same weight, 2g, um, and it's moving up the slope, so friction is still going to be going that way, and normal reaction is still like this, and we've still got theta here and theta here. So that is everything, and I can apply. First of all, I need to get the d is going to be the deceleration. So let's apply F equals ma. Now, because it's moving up the slope, I'll still apply it up the slope, but I'm going to get minus Fr, which is 8 over 5g times this 0.6747 from before. Then I'm going to be minusing the weight, which was my 2g sine theta, or 6 over 5g, and that is going to equal 2 times the new acceleration. Okay, so I use the answer button, keep it exact. You can use fractions, but it's absolutely fine to just do like 6 divided by 5 times 9.8. It's the same thing. Okay, then I'm going to need to divide by 2. So I get minus 11.17. Okay, it's very quick deceleration because the coefficient of friction is pretty sizable. So I just now need to apply suvat and up the slope. I want to find out what S is. So U, now U is going to be 1.2 because we've got the same initial speed. Basically, this is like two different suvat parts. We got the duration of B falling to the ground. Then we had that 0.48. That was one instance of suvat. But as soon as it hits the ground, the string becomes slack, and then B is simply moving up the slope but decelerating. And the final velocity of part one of this set of, part one of the problem where B is falling as it hits the ground, that is when the final velocity was 1.2, so that becomes the initial velocity of the second part. Okay, that's very important. That this quite often comes into these sorts of questions. And then the final velocity is actually here now going to be 0. It's when it stops. We've got A is minus 11.17. So we're nearly there. It's just another case of v squared equals u squared plus 2as. 0, 1.2 squared minus 2 times 11.17s. Rearrange it, we're going to get 1.2 squared divided by 2 times 11.17. Which gives 0.06445. Okay, that is actually going to be about 6.4 centimeters, but I'll leave it to three significant figures in meters. Okay, and there we have it. So I hope you're happy with that. Get the diagram down really carefully, everything we need. Just slowly work your way through it. Be really careful to involve friction and everything. Then part D is sort of your, what happens when it hits the ground kind of problem. Be aware of the initial velocity here and the final velocity. Well done.